everybody. Today we are going to continue talking about ionic compounds. So remember, a compound that forms between a metal or a nonmetal, aka a cation and an anion. A few properties that we haven't really touched on a ton, but we did see this one in class, is burning magnesium with oxygen, right? A metal with a nonmetal. We actually produce MgO, and you remember it was a white powder substance, which was a solid state at room temperature, was a solid. Ionic compounds are generally solid at room temperature, right? So that's true of all ionic compounds, or what we call salts. They're all called salts. They form a repeating arrangement of cations and anions. So we have here a positive, negative, positive, negative, negative, positive, negative, positive, or cation, anion, anion. And they form this structure that we actually call a crystal structure. Notice that they are packed closely together because, again, they're mostly solid state at room temperature. They also are very attracted to each other. They have a very strong attraction between the cation and the anion, or the positive and the negative. And because of that strong attraction, that strong force of attraction, that strong bond, they have relatively high melting or boiling points. So it takes a lot of energy to overcome that force of attraction and actually pull those ions apart by melting or boiling. They also, if they are molten, aka melted down, or if they're dissolved in water, they're actually fairly good conductors of electricity. All right, so now I do want to look at, before we go on to nomenclature, we're going to take a little bit of a look at what I think you'll love, and that is how ionic compounds form, not using electron configuration or Lewis structures, because we've already seen how they form using those, but how about a little shortcut? Who doesn't love a shortcut? And this is what we call the crisscross method, and so that's what I'll typically refer to it as, is the crisscross method, and you'll see why in a second. Now, how to use our shortcut. The first thing, and you're going to use this during this whole video, you'll see it over and over again, no matter what kind of ions we're working with. You're going to write the ion symbol, and you're going to circle the charge number. So, for example, Al3+ would be my ion symbol, and I circle the 3, not the 3+, just the number, the 3. Then we're going to crisscross and reduce. We're going to bring those numbers crisscross down to the other ion, and you'll see that. And then we can write the cation followed by the anion. So Mg2+. I'm going to circle the 2, not the plus. O2-, I'm going to circle the 2. I'm going to circle the charge. I'm going to crisscross and reduce. So crisscross the numbers. And then I can write down here Mg, and I bring that number down that I just crisscrossed, 2. So I have Mg2. And I have O, and I bring that number down that I just crisscrossed, 2. Mg2, O2. Now, that could be the final structure, except we need to make sure that we reduce. Can the 2 and the 2 be reduced? Are they divisible by the same number? Yeah, they're both divisible by 2. So they can actually be reduced to make the compound MgO. One of each, one Mg, one O. And then I've written this with the cation first, the anion second. The metal first, the nonmetal second. Over here with calcium and chloride ion, calcium ion and chloride, again, I'm going to circle the charge number, circle the 2 there. And because there's no charge number here on chloride, we know that it's actually a 1, right? So this is a -1 charge, or a 1- charge. I didn't leave enough room, or I would write it over here. And I'm going to circle that 1. I'm going to crisscross, and I have calcium with a 1. Now, again, the 1 is understood if it's not there, so I'm not going to write a 1. And then chloride has a 2. That's the number that's being crisscrossed down. So my final formula, compound formed, is CaCl2. Now, can I reduce that? I have 1 calcium, 2 chlorides. 1 and 2 are not divisible by the same number. So no, this is not reducible. It's already in the reduced form. So that would be the final formula. So let's take a look at how to use this still, but also how to name compounds. Okay, so we're going to look at nomenclature, and we're going to start off a little bit easier with things that we've kind of seen in class already. And those are what we call binary compounds. So nomenclature just means how to name compounds, so we're going to be naming them. And specifically binary compounds, the bi, what does it mean? It means 2. So binary compounds have only 2 elements in the compound, no more. They have to have at least 2, and they can't have more than 2. So exactly 2 elements in that compound is a binary compound. Now we'll see two different kinds of binary compounds, and we're going to take a look right now at the difference in writing the formula and naming them for the two different kinds. The first kind is a type 1, and these are metals that have only one possible charge. So we've seen in class we can predict the charge of this whole S block and this whole P block. +1, +2, +3, nothing. -3, -2, -1, nothing. Those all have one possible charge, along with a couple other transition metals that are listed on the back of the periodic table under transition metals with only one charge. Those all have one possible charge, and generally they're predicted from the periodic table. So for these, this is what we'd expect. We have a cation, we have an anion, only two. Cation, anion, only two. How we figure out the compound is that crisscross method we just saw. Circle the 2, circle the 1, bring it down, and we get Mg1Cl2. So my compound here is MgCl2. Now to name it, we name it just like we've been naming the ions along the way here. So we're going to name the cation, which is just the metal name, magnesium. Now we would call this magnesium ion, but when we write it in compound, we leave the ion off because we're writing the compound name here. And chloride, we just keep as chloride. Easy enough. Magnesium chloride. For Al3 plus and O2 minus, again, I'm going to circle the charges, crisscross, and I get Al2, O3. 2 and 3 cannot be reduced anymore, so that's my final formula, Al2O3. And again, I'm going to name the cation like I see it, aluminum. And the anion, with the ending "ide", is oxide, right? We've seen this already. This should be pretty basic. Now the type 2 binary compounds are only slightly different, and the difference here is that the metals have 2 or more possible charges, not just one charge, and we're going to see those on the back of the periodic table here. So these are all the monatomic type 2 cations. We've seen the different charges that they can take on, and we've actually boxed those on our periodic table, hopefully. So you know which ones they are. They can have 2 or more possible charges, sometimes 2, sometimes more, and you look on the chart on the back of the periodic table to figure out that charge. It will tell you what the charge is. All right? And then when we're writing the name, we're going to use Roman numerals to indicate what that charge is. Because if you don't use Roman numerals, nobody would know what cation you're working with. So for example, here we go, Fe2 plus and O2 minus. All right, again, crisscross method over here. Circle the 2, crisscross, and I get Fe2O2. Can 2 and 2 be reduced? Yeah, they can be reduced to 1 and 1. So this formula is FeO, 1 Fe, 1 O, right? Because we have to reduce it. And when we name it exactly like we did up here, except we're going to include a Roman numeral to show the different charge that iron has here. So, name the cation. Fe is iron. I'm going to leave room here for parentheses because I need to indicate the charge of that iron. Now, I can see here, iron has a 2 plus. If you're given the name, you just look on the back of the periodic table, find the Roman numeral, and that will tell you the charge. Okay, so iron 2, Roman numeral 2 plus, iron 2. And name that O just like we did above, oxide. And that's it. So the only difference is we're adding a Roman numeral. Down here, Fe3 plus and O2 minus. Again, I'm going to circle the 3, circle the 2, crisscross, and Fe2O3 is what I get. 2 and 3 cannot be reduced. So Fe2O3 is my final compound. And now to name it, I'm going to, again, write the cation like I see it, iron. Got my parentheses there so that I can indicate the charge that the iron takes on. And if you look over there, it's a charge of 3 plus. So this is iron 1, 2, 3, Roman numeral 3. And O is, again, oxide. Okay? So the only difference between iron 2 oxide and iron 3 oxide is the charge on the iron, and therefore the number of iron and oxygen atoms. So that's actually a huge change, and that's why we have to indicate which iron we're working with because it changes the compound entirely, okay? Now, the last one that we're going to look at is how to name ternary compounds. Now, if binary means there's only 2 elements in it, ternary, ter means 3, ternary means that there's 3 or more elements in the compound, okay? So these are going to be a little bit different than what we've just seen. So ternary compounds, the reason they have 3 elements is that they contain a polyatomic ion, which is a group of nonmetal ions, generally, or nonmetal atoms with an overall charge, okay? So we look at the polyatomic ions right here, and we actually see them all listed, both their charge, their formula, their charge, and their name, which makes this really easy for naming. We find those on the back of the periodic table, and then the clues that we have a ternary compound that we're working with, and so that we have to like maybe look on the back of the periodic table to see either the charge or the name, is first, the formula has 3 or more different atoms. So you can see here, there's Na, P, and O. This is a capital O, right? So it's not P lowercase o. This is a capital O, meaning that's a different element. So that's 3 elements, sodium, phosphorus, and oxygen. Here, calcium, chlorine, and oxygen. We have 3 atoms right there as well. Okay, so the other clue is if we have the name ends in either ite or ate instead of IDE, which is how we've been naming up until now. So if the name ends in ite or ate, look on the back of the periodic table and you're going to find the polyatomic ion there. Okay, when we name, we write the cation just like we've been doing the whole time, and then the polyatomic name straight from here, okay? So let's take a look. K plus and SO4 2 minus. I'm going to circle the charges, 1 and 2. I'm going to crisscross, and I get K, 2, right? Bring that 2 down. SO4, 1, okay? Now, again, I'm not writing the 1. I do keep that whole SO4 together. You don't move it. So my formula here is K2, SO4. The name, I'm going to name the metal just like I see it. K is potassium. And then SO4, 2 minus, I can find on the back of the periodic table. Forget where it is. So SO4, 2 minus right here, I see the word sulfate. So this is potassium sulfate, okay? What if I have the name and I don't have the ions or the compound? Well, sodium nitrate, 8 tells me, ATE tells me, look on the back of the periodic table. I know sodium. Sodium's an alkali metal. It's in the first family, so in group 1, so it has a +1 charge. And nitrate, again, I'm going to look on the back of the periodic table. I see nitrate, which is NO3 minus. Okay? And then I can come over here and actually do the crisscross and reduce method, but hopefully you see that if I have 1 plus and 1 minus, the 1s are just going to crisscross to 1. So I'm going to have 1 Na and 1 NO3. I'm not breaking up that NO3, I'm keeping it together. Okay? Now last one, I have aluminum and I have hydrogen chlorate, or hydrogen carbonate here. All right, so aluminum and hydrogen carbonate, I need to figure out what compound they make. So again, I'm going to circle the 3, circle the 1, okay? We're going to crisscross, and I get Al, just 1, HClO, or HCO3, with a 3 down here. Now, if I just put the 3 there without a parentheses, then this is HCO33. That's not what I'm trying to indicate. I'm trying to indicate HCO3, and I have 3 of them. So I put that HCO3 in parentheses to indicate there's 3 of them. So my final compound formula is Al, HCO3, 3. Okay, and my name is aluminum. Name the cation like you see it. And then HCO3, right there, hydrogen carbonate. So aluminum, hydrogen carbonate, and that's it. All right, so there's my full name for all of them. That's it. Hope you have a good day.